A very good evening to all the guests present there. Now, when we talk about natural language processing, that is another complicated domain, as we see, because it deals with the spoken language, the language which we deal with, the human language, which is very complicated. So when a machine is going to process human language to understand it, first of all, then to apply certain logic on it, then this processing is called natural language processing, or NLP. So wherever a machine is dealing with the spoken language or the written word maybe, or the heard word, the word is spoken to it, then that machine or algorithm is called an NLP algorithm. Now, what is the purpose? Why do we need this? Why do we actually need this natural language processing? So when we go into the why part of it, by your own experience, you can answer the question. Like if you look around, there are so many applications related to NLP. Like we commonly use the search. We speak into Google Assistant or we speak into a search engine and search happens. We no more type into the text box. So that is one very common application. Another very common application is when we type in the word into some sort of program, it responds back, like chatbots. In our apps, in our banking apps, in other utility websites, today we have got chatbots who can interpret what has been typed, or there are advanced chatbots who respond in speech. That is one part. So NLP, natural language processing, has one aspect where the spoken word is processed, it is understood. Then if you look at one example, one very common example is Alexa or any digital assistant, which takes the spoken word, understands it, and after that it responds back in the spoken language. That is another aspect. That's called natural language generation. So NLP has two broad aspects: natural language understanding, whatever has been given in form of human language. It could be an audio or it could be typed text. The algorithm should be able to understand what has been given. And second aspect is natural language generation. If the response is going to be spoken word, or the response is going to be some text back to the user, then natural language generation is also important. Natural language understanding is equally complicated equally challenging as natural language generation. Now, when we talk about challenge, how it is challenging? Well, we are the examples ourselves. When we were small kids, we were trying to learn languages. We very easily learned which language? Our mother tongue, because we live in that environment. We can perceive that language easily. It has been all around us. So it was easier for the neurons of our brain to record and synthesize that kind of information. But whenever we are going to learn a different language, English, French, Spanish, like Spanish is one of the most spoken language in the world, French also. So if we are going to learn about it, German. So that's a strange language. That's a new language for us. And it is difficult to interpret, to understand it. Now think of a machine. We human beings can at least figure about grammar, about the sense of the sentence, about multiple meanings of the words, about ambiguous sentences. But think of a machine. Machine does not have that learning, that kind of common sense. So that is one big challenge, where a machine has that common sense to understand the sense out of it. So language, the challenge lies where language has two aspects: syntax and semantics. So syntax relates to the grammar. Now you pick up any language, grammar, it might be complicated, but it has some limitations. It has a boundary, defined boundary. And if we focus on grammar, we can define all the rules which can be used by the algorithm. What these technology giants had been doing for past 10 years, Google, Amazon, Microsoft, since their inception, they are visionaries. They could see through 20 years. So for past decade, what they have been doing, they have been creating those language rules in all the possible languages in the world. Today, they have those 1,000 set of rules which are fed into Alexa. So as far as syntax or grammar of a language is concerned, that can be taken care of. Rules can be created and those rules can be taught to the machine or can be made available to the machine so that machine can refer to them. But what about the semantics? Semantics actually relates to making sense out of the language. So how a machine can distinguish between sarcasm or a normal sentence, how a machine is going to distinguish between multiple meanings of a word used in different contexts, how a machine is going to distinguish between the ambiguous meaning of the sentence. So this all poses challenges for the programmers, for AI programmers, to train the machines into language. And then that is the natural language understanding part. After that, generating the natural language back to the user is another challenge. So because of these semantic complexities of the language, these kind of challenges occur. So as I was talking about natural language processing, we deal with the spoken and written language in this domain. And when we go about wherever it is reached, wherever it is being used, wherever the language is involved in written or spoken form, that makes the application for NLP in AI. So it's recognizing the speech, searching on the basis of text, translating the documents. Sentiment analysis is very common. As we go on social media, we write reviews for the products, we interact with our friends out there on cyberspace. All that data is taken by AI algorithms and they analyze and find out our political inclination, our love for a product, our hate for a product. What do we like? What do we dislike? So that's very helpful for the businesses, the celebrities, the media houses, the political parties, all these organizations. Then information extraction, a very common requirement. A spell check we experience ourselves. Classification of the documents in a digital library, depending on the genres of the documents, classifying them. If you talk about a particular domain of industry, say medical or legal, if you have given all the cases of Supreme Courts in which you have to segregate between civil cases and criminal cases. In criminal cases, you have to particularly segregate the documents related to suicides or murders or a particular kind of crime. So there, text classification, document classification comes in, a very complicated process. Then intent detection, it is just like sentiment analysis. So from the sentence, just figuring what is the intention of the user. So all these are very common applications for NLP, natural language processing. Then we talk about how this sense is made out of the written word. So NLP challenges, some examples, very small examples are given here. If you see the first two sentences, I bought a new watch. So here watch is actually a noun, watch, a gadget. Keep a watch on him, here the watch is verb. So a machine, it's very difficult for a machine to figure whether it's a noun, it's a verb. And you see the third sentence. There again, the watch is verb. We are watching the cricket match. Similarly, there are other ambiguities like he spoke to the girl with a pencil in hand. Whose hand the pencil is in? The person who spoke or the girl? So these kind of ambiguities are very difficult for a machine to figure. He spoke to the boy with a pencil in his hand. Now, more ambiguity here. Which man? The person is speaking or the boy? He looked at the boy red with anger. So who is angry here? So he looked at the boy red in anger. So these are the ambiguities which are posed to the machine. These are the challenges which are posed to the machine. The car hit the wall as it moved. What was moving, the car or the wall? So these are certain examples which you can quote in the classroom to give the example, to just show how ambiguities are there in the language. Then we move on to how this natural language processing actually takes place. So when we get, say, suppose you have got a paragraph you are given and that paragraph has to be processed. Imagine you are an NLP algorithm and you have to process that paragraph to identify, to just find out what has been talked about, what is the topic is about. So how do we go about it? So generally what happens is, when we go for processing the text in natural language processing, what we do is we do something called text vectorization. Now this text vectorization is what? Actually, machines understand numbers, and a set of numbers is called a vector. So whatever language is there, it has to be converted into numbers. So here I'm not talking about binary language. Like if you have written hello, hello can be converted into its binary form. No, not that. What I'm talking about here is converting, finding out what all words are there, how many times they are occurring in the document, if there are multiple documents, in how many documents those words are occurring, and so on. So this kind of statistics is required out of that text, which helps the machine to develop some kind of logic to understand the text and then work on it. So that is called vectorization. When you're converting, when you're taking out the features of the paragraph you are given, the text you are given, and you are translating those features into numbers, then that set of numbers is called vector. For a simple example is, suppose we are given a paragraph about Java programming language. So how many times in that text the term Java has appeared? That is one feature. That's called frequency. So this is one simple feature of a word. So similarly, you will find out what all words are there and how many times they are appearing in that particular document. Then there could be multiple documents. So you are finding out this particular word is appearing in how many documents. There could be certain documents out of that collection in which that word might not have been used at all. So how many documents in a particular document, how many times? These are two features now. So this way, various features of the text are extracted, and depending on those features, machine figures out what to do with it. So text vectorization tools are there. There are certain algorithms, there are certain approaches which help to extract the features of the language, and then those are fed to the machine learning algorithm, NLP algorithm. The machine is trained with those features, and once the machine is trained with those features, it can be used, it can be deployed for NLP application. So what are these text vectorization techniques? So first of all, what we do is the paragraph which has been given to us, the text which is available, it is, as human beings, it is fine. But for a machine, it has to be scaled down. For a machine, that paragraph as it is cannot be used. So we go for certain techniques called text normalization. In text normalization, we go for segmentation, tokenization, and then feature extraction by the help of certain algorithms called bag of words and term frequency and inverse document frequency. So these are certain terms you should be familiar with. So one by one, we will look into these terms and how they are practically used. But before going for feature extraction, before going for actual processing of that text, what we here need is certain things are required. First of all, as I told you, the text normalization has to be done. The text has to be scaled down. How it has to be scaled down? First of all, we remove all the unwanted symbols and things and phrases from it. For example, punctuations. There might be pronouns, prepositions, articles, the, all these has to be removed. Once they are removed, the remaining important words are there. Now, out of this remaining important words, there are certain words which are in different variations. For example, if I take one example like study. So study can be used as studying. In the same text, the word study is appearing as studied. Different tense forms are there. There might be plurals, singular and plurals, man, men, car, cars. So these words have to be stemmed down, they have to be curtailed, they have to be edited or cut down to their basic stem, basic root. So if I say generous, generous in itself is a word, complete word. It cannot be cut down. But if I say generosity, that has to be taken care of. If I say careful, careful, the stem is care. But if I say care, for care, the stem is not car. The care itself is a complete word. So stemming has to be done. After stemming, in certain cases, we do lemmatization also. What is lemmatization? Lemmatization is after stemming a word, giving it the proper meaning. For example, suppose there is a word called study, studying, or studious, or study. So the root is study. Fine. Now, if you take the word studious, it will give you studi, which is not the correct spelling. So it has to be converted into correct spelling. That is called lemmatization. So when you are cutting down a word, when you're editing or curtailing a word, or in simple terms, when you're stemming a word, and after stemming, that word is losing its meaning, and you are adding the meaning to it, bringing it back to the actual correct word, then that is called lemmatization. So stemming is faster. When you go for stemming, if you are doing, say, you are doing text classification, or you are doing any such processing of the text where the response is not to be given back to the user in natural language, in all such areas, you can use only stemming, because it is not going more, it is not going to claim more CPU cycles. It is faster. But when you go for lemmatization, the CPU cycles are higher and it requires more hardware resources to do so. Why? Because AI algorithm has to look for the correct word and substitute the stemmed word with the correct word. Now that is going to take time. So that's why lemmatization is a time-taking process, but wherever you have to respond back to the user in natural language, like in case of Alexa, any digital assistant, a chatbot, there you have to go for lemmatization. So you see the difference in the application. Stemming is required where you just have to process the document, but lemmatization is necessary where you have to respond back in natural language also. So this is one very basic difference between these two and the techniques. And once your text normalization is done, you have removed all the punctuations, you have removed all unwanted words, pronouns, prepositions, articles, and then you have done the stemming or the lemmatization. What you get is normalized text. Now, this normalized text can be converted into a vector of numbers. You can now further process it. So one very important, one very basic approach of extracting feature, as I told you, of some text is bag of words. Now, bag of words approach is very common, and it takes out two features from the text, the vocabulary and the frequency. So as you see on the screen, there are three documents, for example. One document is talking about HTML, another document is talking about Java, and the third one is talking about cascading style sheets. Now, these three documents are completely different in terms of languages. Now, out of this, if I'm going to take out the vocabulary, for example, HTML, how many times HTML is appearing in document 1? How many times in 2 and 3? That is called the vocabulary. The HTML is the vocabulary, and frequency is how many times it is appearing in that particular document. For certain terms, I have taken it out. HTML, Java, CSS. Now, when we are talking about HTML, it might not be necessary that everywhere we are going to talk about HTML by the term HTML. At certain point of time, I will use it or this language instead of the actual term. So I have taken two more terms here, language and it, which are very common. So as you see here in document 1, 2, and 3, the term HTML, Java, CSS, language, and it, they have appeared as shown in this particular table. So you see, we have taken out the vocabulary and we have taken out the frequency document wise. These two features are taken out. That is called bag of words, BOW approach. And this particular arrangement is called document vector. So document vector is nothing but it is a set of numbers which describes how many times some vocabulary has appeared in different documents. So that is BOW approach. Now let us look slightly in detail what this vector is, how this vector is going to be very useful for us. One term is called term frequency. Now, term frequency is the vocabulary, for example, HTML, Java, CSS here, as you see. And frequency is how many times that particular term is appearing in a particular document. So always remember that this term frequency, TF, is document wise. So whenever I'm going to ask a question, I will always ask like this: what is the term frequency of Java in document 2? The answer is 0. What is the term frequency of Java in document 1? So like this, I will calculate. Now, if we pick up term frequency, once we are able to understand term frequency, then we go for something called document frequency. Document frequency means in how many documents out of that collection of documents. Now, this collection of document is technically called corpus. Corpus means a set of documents which we are going to process. So in how many times, in how many documents that term has appeared. There may be 10 documents, but a particular term might have appeared only in 2 documents. That is called document frequency. So term frequency is document wise. In a particular document, how many times that term has appeared. Document frequency is how many times a term has appeared in how many documents. In how many documents the term has appeared. That is document frequency. So these two have to be understood very carefully. Then only we can proceed further. For example, if you see here, HTML is here. If we take the example of HTML in document 1, how many documents are there? 3 documents are there. Document frequency. HTML is appearing only in 1 document. So this is the difference between document frequency and term frequency. Then we move on to something called inverse document frequency. Inverse document frequency is calculated by the help of document frequency and term frequency. How? Inverse document frequency is simply calculated by you first of all take the number of documents. How many documents are there? For example, in our case, the number of documents is 3. And it is divided by the term frequency of that, the term frequency of the term. So if we talk about HTML, the inverse document, how many documents are there? 3 documents are there. And inverse and term frequency for document 1 is 1. So that the IDF for particular document is 3. So for HTML, the inverse document frequency for document 1 is number of documents, that is 3, divided by term frequency of HTML in document 1, that is 1. That gives me 3. So once your inverse document frequency is calculated, you take the log of it. You simply take the log of 10 of that particular resultant, which you have got out of division. And once that log is taken out, like what I have done here is the inverse document frequency of HTML is 3 and the log of 3 is 0.477. Log is taken. After that, you can multiply term frequency with inverse document frequency. For HTML, the term frequency was 3. HTML was appearing 3 times in document 1. So I have taken here 3. And here it is multiplied by with IDF. So that gives me 1.4. 1.4 is the TF-IDF of HTML in this corpus. Similarly, I have done with language. Now, why do we do that? Why do we go for such complicated approach? The reason is when you are processing many documents, there are certain terms which are appearing many times. And there are certain terms which are appearing for a fewer times. For example, document 1 is talking about HTML, but HTML is appearing only 3 times here. Java is appearing only 2 times. CSS is appearing only 2 or 3 times. But the word language is appearing so many times. See, in all the documents, language is appearing so many times. It is also appearing. So language seems to be very, very high. For example, in a medical document, if you're processing a medical corpus of a hospital, the word patient will be coming many times. The word medicine will be coming many times. But both these terms are not important. What might be important is the name of the disease. But patient and medicine, these two terms are appearing so many times, their frequency is so high, it looks that these are the important terms, but they are not. What happens is, whenever the frequency of unnecessary terms is higher in a document, this approach, TF-IDF approach, brings down the importance of those terms. As you see here, HTML has the importance, TF-IDF is the importance. TF-IDF for HTML is 1.4 and TF-IDF of language is how much? 0. It is not important at all. However, language is appearing so many times in all the documents, this term is appearing. So this approach actually reverses the effect. A higher frequency term after TF-IDF goes into lower frequency. And that is why this approach is very useful when we are classifying the text, classifying the documents, trying to identifying the documents. Important terms are useful for you. So this approach is important where not only bag of words will give you frequency. If you look at a particular document, it seems, okay, this term is going to be very important. If this term has higher frequency in this document, so maybe this document is talking about this particular term. Language ka frequency is very high in a particular document. That does not mean that document is talking about language. It is talking about HTML. So for that, bag of words alone is not important. You have to go further to calculate TF-IDF. And this is how do we do. Term frequency, number of term appearing in a particular document. Document frequency, number of documents in which that term is appearing. IDF is number of documents divided by the term frequency. And then TF-IDF is the multiplication of term frequency and inverse document frequency. So this is how you go for calculating TF-IDF. As you see this orange box, some text is given here. And what I have done is I have done some simple normalization. I have removed all the punctuations and I have removed the case also. I have turned the document into lowercase. See, that is also the part of normalization. We bring all the text into simple single case. So this text is same except for punctuations are removed and it is in lowercase. Now, once this is done, this is called text cleaning. After text cleaning, what I have done is I'm going to extract these words. So many words are there, 1, 2, 3, 4, 5, 6. It's a lot of count. So what I'm going to do is I'm going to extract each and every word from this paragraph. See how I'm going to do it. If you see, this paragraph has words separated by single space. Just for the convenience, I have kept it. A paragraph with words, it is just a set of words separated by space. Now, what you have to note here is there is no space before the first word and there is no space after the first word. So I'm going to show you how I'm going to extract each word in Excel. So we are starting from position 1. And we know that the first space is at position 4. How I have done it? So I've simply used a function called search function here. Search function is actually looking for a space. You see, double quote, space, double quote. I am searching a space in which text? G10. G10 is the cell in which that sentence, that text is there. From where I want to start my search, I want to start my search from the very beginning. That is position 1. So 3 things I have to tell search: what to search, where to search, and from where to start the search. So what to search is a space, where to search is the text, is the cell address in which the text is there, and from where to begin the search is, I have mentioned here, from 1. So when I do this, I get the position of the space. See, I get the position of the first space. The first space is the 4th letter. The first 2 letters were THE. See, 1, 2, 3, 4. 4 is the position of the first space. I got the position of the first space. Now this will help me in extracting this word, the. How I'm going to extract this? I'm going to use mid function. Mid function is used to extract a particular text from the given text. Here I want to extract the first letter, THE, the. So what I'm going to give to mid? First of all, I'm going to give to mid in which text I have to look for. That is in cell G10. In cell G10, the entire text is available. Then I have to tell mid from which position the text extraction should begin. That position is 1 because THE, the, is the first letter. So that position is 1. And then I have to tell mid function up till when I should stop extracting. How many letters have to be extracted? So for that, I have given the position 4. 4 is the position of the space. THE, T 1 par hai, H is at 2, E is at 3, space is at 4. So I want my mid to stop at 4. So from 1 to 3, it will take out. See, in text G10, it will look from position 1 till position 4, and it will extract only THE. When I press enter, I get my key here. Well and good. So first of all, I found the position of the next space, and then using these two information, using these two as boundary in mid function, I extract the particular word. Now first space is done. Second space is coming after the second word. Here you have to keep in mind that spaces are coming after the word. Now what is the next position? First space is at position 4. The second word is going to start from position 5. So I'm doing what? In the next cell, I'm just adding 1 to it. See, I have just added 1 to the previous space position. I have added 1. This will give me the position of the next word immediately after the space, the starting letter. And how will I calculate the boundary of that word, the next space which is appearing after that word? I am again going to use search. And what I'm searching, remember search syntax, what to search, you are searching for a space, where to search in G10, and up till where you have to search D22, from where you have to start the search, sorry. From where you have to start the search is D22 now, not from 1. Start from 5. 5 is the position of the next second word in the text. So it will definitely find the second space. Second space position is 10. And then I use this information in mid. In the text G10, start from D22, start from position 5 and till position 10, take out the letters and I get green. And with this logic, if I copy it down, I get all my words separately. This is the vocabulary. I'm creating bag of words. So from this text, with a simple formula, I have taken out the vocabulary of the document. Now, there is one thing you have to keep in mind. The last word is boxes. And after boxes, there is no space. If you're going to do search, actually, it would be erroneous. It will give some error. So what you do is, whenever you are searching in for the last word, you just put everything into if error. If error function actually works when there is an error in your formula. And if some error is coming, this was your actual formula. See, this is what you are doing actually. You are searching for a space. But in the last word, since there is no space after the last word, our search function will fail. It will return an error. So in that case, what we will do is, how do we calculate the position for mid? What we will do is, we will put this search into if error. If error takes the formula, and if this formula is going to return an error, what action we have to take is the second part. So what I will do is, I'm saying search for the space, and if there is an error in the formula, or in other words, if there is no space found, then what you do is, you take the length of entire text. The length of entire text is the number of characters in the text plus 1. Plus 1 means last word, say from last word, one more position. Now this will give me the position for mid function. And when I will use mid function now, it will work fine. So this is small if error you have to add in your last word search. That's a plain and simple logic. So this logic will come from your computer science logic. You have been teaching computers for long. So this is all the programming approach I'm using in Excel. Nothing special. What we have got now is the words extracted it as a vocabulary set. Now what we are going to do, we are going to find out how many times this particular word has appeared in this text. How do we do that? Let us go for calculating this. So first of all, what I have done is, I have copied all this text. Once I have got this text here, I copied all the text. I said copy, and then separately I right clicked here, and here I did not say paste. I said paste special. In paste special, I have to paste this as text. So when you paste it as text, it will come in plain text. You see the green, now it is plain text. Here what it was formula. It was not the value, but now we have got the value. With paste special, you get all the values here. Once you have got all the values, you select all these values and remove the duplicates. Remember, we have to find the frequency of each word. That means if a word is appearing many times, like the word the is appearing many times. See here, the is appearing here also. It is appearing here also. Here also. So there are certain words which are appearing multiple times. I want unique appearance. So what I did is, after pasting the values here, the words as value here, what I do is I select all of them. I go to data tab. I go to data tab in Excel, and I click on remove duplicates. When I click on remove duplicates, all the duplicate words will be removed, and only unique values will remain. Simple. Remove duplicates. No programming required. You can use remove duplicates. Data tab, remove duplicates. So what you will get here is unique set of words. Now I have to count each word, how many times it is appearing. Like the is appearing 4 times. How did I do it? I use simple count ifs. See, count ifs function, what it does is, first of all, it will take the range of all the cells which are containing the text. So it will take the range of all the words which are there in your collection. These are the words. You see these yellow cells? This range you have to select. I have selected this range, and this is the first parameter into this function. So countifs will always look for this set of words. And in this set of words, it will find out the given word. H21 is this, the. And then this word will be searched here, and as many times it is appearing, that count is taken. The same thing will happen for next word. In the same range, green will be counted. Then in the same range, the word box will be counted, and so on. You can copy down this formula, and as you see, the frequency is taken out. This is your bag of words. Your bag of words implemented in Excel. Then we go to, I'll show you some slightly advanced part, if you are interested, it is just not necessary, but I just want to show you if you are curious enough. I told you that I have removed all the punctuations from here, and then I got this text cleaned. The text cleaning is done by the lower function. Lower function is converting all the letters into lowercase. This is one thing. But how did I remove these punctuations? For removing these punctuations, I had written a separate macro. I'll give you this program. The macro is written here. 1, 2, 3, 4, 5. This 5-line program is actually telling my Excel that remove all the punctuations from this. So only the pattern A to Z and 0 to 9 and space. What I have told this, if you are familiar about regular expression logic, regular expressions are all the symbols which are there in language. So what I have done is, I'm just telling you the logic, the program I will give you, it will run, and the logic I'm giving you here. What I have told my program is to look for A to Z. Any letter from A to Z, that has to be kept. Any letter from 0 to 9, the number, that has to be kept. If there are any spaces, that have to be kept. So ignore this. Anything other than that, remove it. So what I have got is, the text which I have got will be having spaces, A, B, C, D, and any numbers only. Rest, everything is removed. And that text is returned. So I have named my function as clean text. So clean text function will always give me a text which has only alphabets and numbers. That simple logic I have applied. So you see here, clean text function I had written. And in clean text function, I have passed this G1. G1 is the orange cell. And after that, lower function is converting all into lowercase. This is what I got. No comma, no full stops. So this way, suppose I put a double quote here. You see, there is no double quote here. Double quote is removed. I put an exclamation sign here. It is not here. So only alphabets and numbers are taken out. Rest, everything is discarded. So that macro, small 5-line macro, is just doing that. So just for a curiosity, I showed you. So this is how bag of words works. Now we go for TF-IDF. By using simple formulae, you can go for, and a little bit of manual work, we can show simple TF-IDF also in Excel. So in this full demo, I have given bag of word, full demo is here. The text is there, the clean text is there. And see, everything is here. I have even made a data visualization. I made a chart which is showing me which terms are of higher frequency and which are not. So you can create a chart also just to visualize. So this complete example I will give you. That is your bag of words. Now we come to TF-IDF. In TF-IDF, as I told you, the words which are of very high frequency in the document, they get lesser importance, isn't it? Because those words could be stop words. Stop words, the term which is used for the words which are not necessary, the articles, pronouns, and all that. So here I have taken, for TF-IDF, I have taken 3 documents. Do not get intimidated by the descriptive design. I will intercept it for you one by one, and it is very easy actually. It is using all those techniques which I have showed you in bag of words just now. The same techniques are there. There are 3 documents. These documents are talking about something. I don't know. We don't know what it is talking about. Some sentences there. And I have just cleaned the sentences manually. No formula I have applied here. I have just taken out the important words. Green box, big, red box, big, green box, big, red box. So this I have taken out. Now for each document, by applying the same formula, search and mid, search, mid, search, mid. In the last cell, for the last word I have used if error. I have taken out the words separately. For all the documents, I have taken out the words separately, like I did in bag of word. After that, I have copied down these words here and I went to data, remove duplicates. I removed all the duplicate words. So this is what I got. So unique words are there in doc 1, doc 2, and doc 3. Now, out of these unique words, by using countifs, I have taken out the frequency in each document, how many times green, box, and all these terms are appearing in the document. This I have taken out. Once I have taken this out, now these are, document frequencies. For doc 1, green has document frequency 1, and like this. Then I have created the document vector table. Doc 1, doc 2, doc 3, 1, 2, it is just like I have taken all these words. Green, here it is 2 times, here it is 1 time. Box is taken, big is taken, red is taken. Out of these 4 words, in each document, how many times it is appearing, this I have taken out. And I have taken out the document frequency. In which document, how many times? I have done simple countif. So in countif, what I have done, I had simply counted if the value is more than 0, just take it into count. So green document frequency for green is 2. Green is appearing in 2 documents. See, document 1 and document 3. Box is appearing in all the 3 documents. So as you see, green has very less document frequency anyway. So this is how you calculate the document frequency, number of documents, by the help of countif. I come down further, total number of documents is 3. Now what I have done is, I have taken the inverse document frequency, IDF. IDF is number of documents upon document frequency. So after applying that formula, I got 1.5111 like this. Then I took the log. Now the moment I took the log, these are the values. And when I multiply this log value with the term frequency, these are the TF-IDF of all the terms. So you see, TF-IDF of all the terms, box, big, and red, they are important. They have got the TF-IDF 1. See, they are important. Green is lesser important. It is comparatively less important. So just to show you by an example how TF-IDF is calculated, there is another example here talking about HTML language. Here language term is very high. Language has a lot of frequency. Language, 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 and language. See, language is appearing so many times. It looks like language is a very important term. But after applying all the logic, taking out the unique words, taking out the bag of words, taking out the document frequency, calculating the IDF, and then calculating the log, when I come down to TF-IDF, our language term, which was very frequent, has got TF-IDF 0. TF-IDF 0 means it is not important. What is important is HTML, program, and other terms. Markup, document, describe, these are important, but language, which had very high frequency, has come down to 0. So this is how TF-IDF functions. I launch Jupyter Notebook from Anaconda. So first of all, if you're importing NLTK, now this is Natural Language Toolkit from Python. This is the library which helps you performing natural language processing. If you're importing it and if you're not, it is not available, you can just give the command nltk.download. And if you want any Indian domain, Indian collection of words, you can mention Indian like this, and it will download NLTK library here. Sentence tokenization. Sentence tokenization means breaking the text into sentences. So here, from NLTK tokenize package, NLTK has got a package called tokenize. From this package, I'm importing a function called sent tokenize. Sent tokenize stands for sentence tokenization. I have some text here, and this Sent tokenize is given this text, and all the sentences are broken down into separate sentences, and a list of those sentences is given. See, here is the output. You see the comma here and the comma here. 3 sentences are now available in the list, which I can use further. Now, for word tokenization, I can break entire text into words also. Word tokenize is also in the same package. I have given the text to a function word tokenize. It has given me the list of all the words separately. See, so many commas in Satyagraha, comma, there is no place for fraud. So all the words I have taken out. I can find out the frequency of each word by the help of FREQDIST, frequency distribution function, FREQDIST. This function is available in another package of NLTK, that is probability. From probability package, you import FREQDIST class and you use this FREQDIST. Whatever words you have tokenized, they are in the list tokens. This is a list of all the words separate. This list is given to the function FREQDIST, and it has given me all the frequencies of those words. There is another very important library in NLTK corpus package. You import stop words. Stop words will give you all the possible stop words in English language. So stop words is a collection of all the stop words, not only in English language, you can use it for other languages also. So here what I have done is stop words ka words function is used, and I'm passing English language here. So it will take out all the English language stop words and create a collection called set. You know, list and set. List can be modified, set cannot be modified. That's the only difference. Otherwise, it is a set of values. So it will load all the stop words in English language into a collection called set, a list of all the stop words. That list is available here, and it is simply printed here. So in this text, if you deduct one set of tokens from another set of stop words, these are the words which are without stop words. They have been taken out. So this way, stop words can be filtered. Your text can be filtered from the stop words of English language. Similarly, you have a corpus of Indian words also. You import NLTK. In corpus package, Indian package, words, you say hindi.pos, and if you display each word, this is the corpus of all the Indian words. These are all the stop words. This program is taken using English keyword, and it is taking out all the stop words of English language, and it is printing it here. These are all the words, stop words which are there in English language, most of them. So this way, you can show that you can demonstrate that already the work has been done. The people who have developed Python and the people who are developing libraries for NLP, they have already done a lot of work for you. You have to just bring it together and perform your NLP exercise. So this demo will show you basic tokenization and how to remove stop words, what all common stop words are there in English language. This example will show you. Now you have to demonstrate stemming and lemmatization to the students. This example will show you. If you see, from NLTK package, from NLTK library, I have taken out a package stem. And from stem, I have imported an algorithm called Porter stemmer. Porter stemmer is an algorithm. It is implemented as a part of, as an object in Python. You can just take it, you can import it, and you can use it. How? You simply, just for the demo, I have taken a list of words. These are very common words. See, caring, care, cars, careful, honesty, honestly, studied, studying, studied. Studied has come 2 times. Doesn't matter. Formation, formation, or I make it format. Formation, format, formal. These common words I have taken, just some repeating words. and see the result of stemming. So did you see how stemming is done? Care. From cars, it has taken out car. Care is wala care. Second wala care. Its stemming has not been done, not required. See the stemming of honesty, study, format. So the words have been reduced down to their stem, the actual stem. That's called stemming. Now, if we go for lemmatization, there is another algorithm. One is Porter stemmer algorithm. Similarly, there is another algorithm called snowball. Snowball stemmer algorithm is also there for stemming. But snowball stemmer is very powerful because it does stemming not only in English language, it does in other languages also. So when you have a list of words to stem, what you do is you call snowball stemmer construct and you have to mention which language. Otherwise, it will not work. So you just mention English in all lowercase. That means English language, and it will give you all the stemmed words. See, generation, generator, generous, generate. See, generous, it is very intelligent. It has not done stemming for generous because generous is a word, whole word in itself. Car park, it has not done stemming. For care, it has not done, for careful, it has done the stemming care. So this is how you can demonstrate stemming. Then for lemmatization, first of all, you run this command nltk.download wordnet. So wordnet collection will download. Wordnet collection is required because it contains all the words which are to be matched for lemmatization. So it has got all the correct words of English language which can be used to replace the stemmed word. After stemming, word does not have the meaning. So it can be replaced with the correct word from this collection. So WordNet has to be downloaded. Once it is downloaded, you can comment it. And then you can run this program. WordNet Lemmatizer. We import this from stem package of NLTK library. You have these words here. You run WordNet Lemmatizer. And what will happen? WordNet Lemmatizer, an instance of WordNet Lemmatizer is created by the name WNL. With WNL instance or object, you call a method called lemmatize. Lemmatize method is defined already in WordNet Lemmatizer. You have to call it here. So first of all, you have created an object of WordNet Lemmatizer by the name WNL. On that object, you have called the method lemmatize. In this lemmatize, you pass this list of your words, your tokens, and it will generate the list of lemmatized words. And that list by the simple for loop is being displayed here. See the lemmatization. Generation, only S is removed. Generators, S is removed. Generous, no lemmatization happened. Expresses, express. Car parkings, car parkings. Eating, eatery, ate. Go, gone, Goa. See, for Goa, it has not done go. It has kept Goa. So this way, very intelligently, lemmatization is done and all the words have meaning. None of the words are without any meaning. But if you look for lemmatization, eatery, generate, these are words without meaning. Here, studi, honestly, these are the words without meaning. But lemmatization has done exactly the words with meanings. So this is what you can demonstrate to your students in classroom as stemming and lemmatization, and they can see practically the difference between the two. And why lemmatization is important, now you can figure that when you have to respond back in natural language, lemmatization is important because you need the correct word to speak. You need the correct word to type. So lemmatization is important for chatbots, for digital assistants, where interaction in natural language is happening between a human being and a machine, or maybe between two machines. So friends, this is what I wanted to show you. Thanks a lot for attending this session.